In this lecture, we're going to talk about DNS-based attacks and their mitigations. So we need to understand what domain name service or DNS, and DNS itself has the hierarchy. We'll see what they are. And one of very popular, very famous attacks based on DNS is Kaminsky attack. Kaminsky is, you know, as, proposed by Dan Kaminsky in 2008. And it's a very, very famous attack, so you need to understand how this works. And also we will deal with farming, cyber squatting, phishing, internet censorship, and one of the mitigations, which is DNSSEC. So what is the domain name system? Um, the main idea is that a human cannot remember all the IP addresses. So if we remember the IP version 4, even though we are using IP version 6 as well, it consists of 32-bit machine. I'm sorry, 32 bits digits, but we cannot remember all the IP addresses. Instead, we need some domain names that can be, easily remembered. So this could be a phone book for the internet. So, for example, suppose that a client says, I want to connect to cs.skku.edu. Then it's easy to remember CS representing computer science and skku.edu. And the DNS server says, here is its IP address, 115.145. Something like that. So how does this work? Somehow we need a server, DNS server, that converts this domain name to IP address. And the current scheme of domain name system is a distributed, hierarchical, and reliable database. It can be actually replaced by the manually maintained ets/ets/host file if you are using Linux. So here, cat etc host, then it actually has the IP address and corresponding URL or domain name here. So the first thing that your machine considers is this host file. So if you are using the Linux machine, then ets host is the file that is referred to by your host. So if you manually insert an IP address with domain name here, then directly connect this domain name into that specific IP address. So this is one of the known way. Let me enlarge this thing. Okay. Can I enlarge this? Okay, like this. So the malware, there are malware that tries to, change this host file. In Windows, let me check. In Windows, you open the Explorer, you go to the C drive, and here go to the Windows and System 32 and drivers, and you can actually see maybe etc here. There is the host I would say in this path, you can see the host file like this. If you open this host file, you can see IP address and domain name there. Let's see. You look at see this file. This is a sample host file used by Microsoft. For example, you can add your own IP address with a specific domain. Then the first DNS lookup refers to this host file. So if this host file is corrupted, then maybe your domain may be corrupted as well. Okay, so this is a very important file. So let's go back. Now, wait. Oh, here. So now, where is this IP address? I mean, where are these domain names managed? And these domain names are assigned by registrars and accredited by ICANN. So this is the organization that manages IP addresses. I think under this organization there is the authority IANA, or Internet Assigned Numbers Authority, and domain names are different kinds of registrars. So if you want to register your own domain name, say google.com, naver.com, so these domain names should be registered in advance with the registrars. And not necessarily domain name is one-to-one mapping with the IP address. So it could be because of the virtual hosting, many different domain names hosted on a single IP address can be, many different domain names can be mapped into a single IP address. And because of load balancing and fault tolerance, a single name can be mapped into multiple IP addresses. So here, load balancing means that you have one domain name and we have two different routers, something like that. Here you can have multiple IP addresses, IP1, IP2, IP3, IP4, and these are the load balancing routers. So load balancing means if something happens, say DOS, and this network has been disconnected, then automatically it switches into the other router so that you can guarantee the availability of the service, right? So it's possible to contain multiple IP addresses for load balancing or fault tolerance with a single domain name, and vice versa. So let's talk about the hierarchy of domain name server. So what is the hierarchical structure here? It can divide into several namespace. So here, if let's consider cs.skku.edu, and this is the largest domain, and the next thing is the skku, and the next thing you can see is cs, and this consists of a hierarchy. And actually, this part, the last part, is managed by root name servers. And this root name server is responsible for top level domain. And this is one of the top level domain, like .com, .edu, .net, .acc.kr, and other country domain. It actually points to the authoritative name server of each TLD. which is managed by government or commercial organizations, not necessarily commercial or just non-commercial organizations as well. So, for example, .edu, .edu points to what is the authoritative name server for SKKU. Maybe skku.edu will handle this, right? So .edu points to skku.edu, and skku.edu name server is managed by Sungkyunkwan University. Well, if you are curious about how many such root, top level domains with this simple command, you can actually get the number of domains. So by having this command line, you get 140, sorry, 1480 different domains. So if you really want to what they are, you can actually look up here. So these are the different kind of domains, top level domains. Maybe .com should be here, right? .com, Comcast. These are different kind of TLD. And authoritative name servers are responsible for a set of names belonging to a zone. And a lift jump here in the DNS hierarchy manages the zone of a single domain. Let's see what this means. In order to reserve the DNS, here reserving means in order to obtain the appropriate IP address that corresponds to domain name, and you should query domain name servers and reserve the requested resource. And there are three main query types. One is non-recursive type, and recursive type, and iterative type. So here, non-recursive type is a query, single server, and receive a response. And it may be a partial response. So meaning it might not be complete. And recursive type is a query, is to query a single server, and then query other domain name servers on behalf of the requester. And here, iterative type is a query with a chain of one or more DNS servers. And each server returns the best answer it has. And if the server cannot find an exact match, and it returns a referrer. Referrer means a pointer to a server authoritative of a lower level of domain namespace. Let's see what this means. So here, suppose that your computer has several different kinds of applications, mail client and web browser. Your operating system maintains a DNS reserver, and the DNS reserver maintains the local cache here, and your computer has the configuration of the DNS server. And DNS server is pointing to here, right? If you set up the DNS server and the DNS, your ISP has the DNS reserver. One of the famous DNS reserver in Google is 8.8.8.8. I think some of you guys use this DNS reserver. What does this reserver do? it recursively do the DNS research on behalf of you. And I think, if I remember correctly, the KT, Korea Telecom, so DNS reserver is 168.126.61.1 and 2. These are all the DNS reservers. Also, the DNS reserver maintains a local cache as well. Anyways, applications place a resolution request to the stub reserver of the operating system. And the stub reserver then typically sends DNS queries to a recursive reserver. So in this case, this guy is a recursive reserver. And if the recursive reserver cannot find the answer in a local storage, in a cache, then it actually recursively query to the domain name server. If it actually finds the information, domain name information in the cache, then it promptly responds the information to your computer localhost. And if the new information has been obtained, then these informations are cached for future queries. And the owner can specify TTL or time to live. So, for example, if you set up 1 hour TTL, then that information can be alive in a local cache for an hour. Typically, this is set to 24 hours or more. And it's possible that negative responses are cached as well. Because if you think about DNS, it doesn't have also authentication mechanism. And the reason of using cache is to save your time, okay? Because it can give you the very quick response. So let's see how the recursive reserver works. A host, a list know one local DNS recursive reserver. So how can we do that? So here you can actually look up your name server with the ns lookup command. If you look up, type this ns lookup command, you get this line, and you can configure the server name. Here the server means your name server, the recursive name server. This can be set 8.8.8.8, which is Google's server. And here 53 is the port number. Usually port 53 is for UDP, for DNS. Now you set up the name server, and then now you can actually look up the domain name. So suppose that what is the cs.skku.edu, then this 8.8.8.8, this lookup server, recursive server, responsive with the non-authoritative answer csskku.edu. Canonical name would be, it's just an optional name, and the address is 115 point something. This means this is not the answer from the name server from SKKU. Instead, this Google server has the cache. That's why it gives you non-authoritative answer. We could switch another name server like this one, and then you can do the same thing. skku.edu. We get the non-authoritative answer as well. And then let's quit. right? So let's see how the recursive reserver works. So now here we have the client, how the hierarchy works of zones and delegations to respond to queries for which it is not authoritative. So it actually asks to the local recursive DNS reserver, what is the IP address of cs.skku.edu? Then this DNS reserver, on behalf of this client, it goes to the root DNS server, asking, okay, what is the IP address of the cs.skku.edu? And the root DNS server, all right, consort with the name server.edu. Then recursive domain name server recursively again ask this name server. All right, what is cs.skku.edu's IP address? And the edu DNS server responding, okay, you should consort with the name server managed by skku.edu. And again, recursive server recursively asks the question inquiring the IP address of the same domain, and the skku.edu, maybe probably name server, 성균관 University's name server is an authoritative server, responding, all right, we know the IP address of the cs.skku.edu, and this IP address is back to the client. And here the local recursive server actually has the cache, has the information in the cache, right? How can we observe this one here? You can actually do this with the dig command, dig trace with the skku.edu. Then you can actually see the actual responses from the root servers. So this command means that trace everything if you want to do the recursive DNS lookup. So actually on the internet, interestingly, we have 13 root servers. Names a.rootservers.net, b.c. until kh. I don't know. You have 13 different kinds of alphabet. These are name servers. This is a pretty important name servers, right? If all the root name servers are down somehow because of DDoS attacks or something, then the complete the internet domain system will be collapsed. Okay, let's look at the next one. Actually, the domain, the recursive, here, recursive DNS reserver received a message from the root server. One of the root servers here received 153 bytes from this guy. I don't know which root server is this one. Within 88 milliseconds. Who is the who has the who knows the cs.skku.edu's IP address and the eduservice.net, this name server? It looks like 13 edu servers as well. It response is okay, gives you consort with the nameserve.skku.ac.kr. This is actually the name server managed by skku.ac.kr. Who answered this? m.rootservers.net actual response is okay. Here, ns.skkuac.kr will let you know the IP address of cs.skku.edu, right? Now, here the authoritative, the name server responses, that's the IP address of something, right? So these are the recursive the answers. You can actually trace all the messages. But the thing, okay, And let's briefly look at the DNS message format here. As I said, mostly DNS uses the UDP port 53, and sometimes TCP can be used for joint transfers. So what is joint transfer? If, as I said, DNS server is very important, right? So usually we have the multiple DNS servers. Say one of the DNS server is working as a backup. Then between this DNS server 1 and 2 as a backup, sometimes it's required to synchronize the database of this DNS, right? And then this synchronization is very important, and the package should be reliable. That's why we use TCP. And syncing this database is called joint transfer. So for the joint transfer, TCP is used other than joint transfer, mostly when you type HTTP slash and what is the domain name for the IP address for certain domain name, then you use the UDP. And recent developments sometimes utilize either TLS or HTTPS with different port, 8053 or 443, but it's not widely used as far as I know. and here are DNS messages. So here are these are important messages. What is RR? If you go to the next slide, RR represent resource record. So these are resource records, important information about the domain name. So it contains question, what is this domain's IP? And it contains answer, what is the authority? If any additional information, you can, additional field contains those information. And this is DNS header for reference. The resource record contains very important information. So there are several different fields. Here, name, type. Type usually is in a numeric form. For example, 15 means MX. We'll see what MX stands for. So it contains the R type, and class means class code, TTL, time to live, the count of seconds, the RR stays valid, and length and data. So there are several types of resource records, or RR. DNS is a generic directory service for other host-related information, right? So what is the host address? It replies with the resource record of A. NS meaning authoritative name server, and MX means a mail server of the domain. And if there are some alias for other names, which is not IP address, the record RR should contain the CNAME. And this pointer is for reverse lookup that maps IP addresses to domain name, and some arbitrary data within the txt RR field, and other host information with the hinfo resource record. So there are several different kinds of types for resource records. But the thing is that the reason why we talked about this is to understand DNS spoofing. And the fundamental cause of DNS spoofing or DNS cache poisoning is because of no authentication, meaning that the responses can be spoofed So earlier we talked about cache poisoning, ARP cache poisoning. Cache is a temporal storage. So if an attacker um, has a power to, somehow overwrite the information that is poisoning, then, you can spoof the message, the information in the cache. As we can see, the local recursive DNS resolver also maintains the cache, and attackers can actually compromise this cache. In other words, an adversary can point to a different address of attackers choosing. The attackers wants phishing or wants a victim to infect the malware or want to do the man-in-the-middle attack. So let's see how this works. To understand DNS poisoning, we should be able to figure out different vantage points. So there are three different kinds of vantage points. We already talked about on-path and in-path, right? So on-path meaning the man on the side, whereas the in-path is man in the middle attack. And off-path is a blind attack, where attackers cannot observe any DNS messages. So the only thing the attacker can do is to inject the blind packets. The best thing that attacker can do is to guess the proper values in the forge's DNS response fields according to the query. And it requires race condition, right? When a user requests DNS message, then the forged response must be arrived before the original packet arrives, right? And this is the same with on-path vantage point. Here, attackers can passively observe the traffic, say DNS queries, and then inject properly forged responses. So if you think about the injecting the reset message, something like that. And it's very easy to mount, particularly in Wi-Fi networks. And it also requires the race condition, like off-path. The forged response generated by an attacker also should be arrived before the real packet arrives, right? For in-path attackers, he could block responses from reaching the victim and manipulate the message in the middle. And attacker can do so much more. Think about the ARP cache poisoning. One more thing we need to know is the transaction ID of the DNS mechanism. And this is the synchronization mechanism between clients and servers. When a client sends the DNS query to the server, it actually goes with the transaction ID, and then the DNS server responds with the transaction ID. And this transaction ID is a 16-bit transaction identifier, and it is randomly chosen for each query. And the response is going to be accepted only when a transaction ID is matched, and then the response will be cached according to time to live. Again, as I said, attackers should be able to win a race by guessing the correct transaction ID. And also the response source IP and destination port should be matched query destination IP and source port. And this is if this is a slightly, it's not that difficult. Back in 2008, we'll see why this attack was viable. And this attack is called the Kaminsky attack. Again, so far we deeply understand how the DNS works. Now let's see how the Kaminsky attack works. This attack, the objective of this attack is to poison a DNS server's cache entry. For say example.com, it cannot just send a random DNS package to the recursive domain name server, and the server will only accept responses to pending queries, right? So because the server is waiting for the request, right? If the attacker cannot predict the right request, then he cannot get any useful message. But if you really think about this carefully, the requirements for a successful response is rather than difficult but slightly trivial. Let's say, what is the probability of matching source and destination IP address? It's easy. What is the matching source and destination UDP port? Well, all the DNS servers use 53 for source port 2. Now it's not, but it could be easily inferred if it changes predictably. And attackers should be able to match transaction ID because it has their 16 bits of randomness, 2 to the power 16. It's around 64K, right? And it should match a question section, meaning that the attacker targets a particular recursive server and thus can trigger a query at will. Let's see what this means. And there is an additional issue. Maybe for the domain example.com, the host of www.example.com may already be in the recursive cache. So when an attacker wants to compromise this domain in the cache, in that case, the recursive will not ask the authoritative. Instead, the recursive server responds the information in the cache, right? So look at this. It's not that difficult. So first thing an attackers do is query the recursive server with any subdomain that is not in the cache, say foo1.example.com. Non-existent subdomains are fine. If the name server cannot find this information in the cache, anyways, the name server, the recursive name server, will ask this domain to the example.com or recursively from the root server, right? And this is not affected by time to live because foo1.example.com is not in the cache. Always the recursive server is trying to reserve this name, foo1.example.com, for example. And it causes the targeted reserver to query authoritative server for the request subdomain. Why is it important? Now, the attacker floods the reserver with many forged responses. Why? Each can contain different guesses of query's transaction ID. So if it's possible to guess the right transaction ID by looking at different queries, then attackers can successfully predict the transaction ID. But another thing is that the attacker should win the race. If the race is lost, and then what happened? Then attacker can do repeat with a different subdomain again and again. It's very easy to query a fake domain, right? Say foo2, foo3, foo4. Then every single time you see the query transaction ID, and then you can forge the DNS packet response. Sorry. So what is the insight from the Kaminsky attack? The recursive name server will always contact the authority of example.com for any lookup of a non-existent domain. This is the key, right? And then attacker can poison the cache with values in the additional RR field, right? And today's internet speed is sufficiently fast enough to flood the server with thousands of packets before the real response arrives. This means attackers can, receive more than enough transaction ID guesses. What is the fix of the Kaminsky attack? This is because of the proper transaction ID guesses. And if you could randomize the UDP port, then attackers should predict UDP port as well. This is the simple fix. And if you combine the randomization of transaction ID, which is 2 to the 16, with the UDP port 2 to the 32, slightly slower than that, I guess, right? Because of the reserved port, well-known ports. If you combine these two cases, then the possibility of right predictability would be orders of magnitude higher difficulty because of higher entropy. So this is one of the master read postings, an illustrated guide to the Kaminsky DNS vulnerability. So if you click this link, now you see use unixwiz.net is unstable. I think this is because this site does not support HTTPS. I think the other day we talked about the HTTP SSL TLS, right? And if you click, I'm going to move this site, then it moves to this website with HTTP itself without encrypting the pages. And this is the Dan Kaminsky. And I think this posting very well explained how this attack works. So it explains very well DNS packets and how this attack works, and what are the resource record types, something like that. So I strongly recommend you to read this posting in order to fully understand how the Kaminsky attack works. Actually, back then, 2008, it was a big security news. That was the serious vulnerability, and that can you know give a huge impact on internet. Okay, let's talk about farming a little bit. What is farming? Farming is traffic redirection at the client side, mostly because of malware that attempts to change DNS setting. And as I said, the malware tries to change the entries in this host file, and when the browser look up your domain name, the first thing that the web browser refers to is this file. So if any name, a domain name and IP address are configured in this file, then it doesn't, give any DNS request. And for example, DNS changer, this malware affects, a lot of different hosts. The estimated value, the estimated number of infected computers is almost 4 million, which gives almost a 14 million profit. And also, dynamic farming. This is allows one to quickly switch the mapping of the legitimate domain between a malicious and real IP. And this dynamic farming technique is also known as DNS rebinding, and this can be served with a malicious script and then switch to the real site. And same origin policy can be bypassed with this dynamic farming technique. We'll get to what the same origin policy in the web security as well. Cyber squatting is another, domain-based attacks. I think you encounter URLs or domain names with very similar benign domain names, like instead of PayPal, the last L is replaced with one in the pal1.com, and sometimes common misspelling there instead of Google, Google, golge.com, and M is missing at the end in this case, and using the entire paypal.com, but it appends -secure.com at the end instead of the Amazon, and between A and Amazon you insert dot, so something like that. These are the cyber squatting attack with seemingly similar domains. And this is called one of the cyber squatting is typo squatting. Here it uses typos, including a common misspelling, abuse of top-level domain, plural of domain, like instead of google.com, a googlez.com, and extra periods like this. And this is also called URL hijacking. And this type of squatting relies on users' mistakes, mistakenly typed spelling. And combo squatting involves no misspelling, but appending an arbitrary word that appears with it, like PayPal-secure.com. And these cyber squatting are mostly for phishing attacks. These two are phishing attacks. Speaking of phishing, what is phishing? Phishing is the term that combines private data with phishing. It it actually sends privately sends a message by email or messengers from a seemingly trusted party, and it tries to convince the victim into revealing variable information, critical information, sensitive information like users' credentials. And typically it contains a malicious link with the cyber squatting domain names or attachment tries to, a victim, so that the victim opens the attachments. The main goal of phishing is to steal users' credentials, username, and passwords mostly. The property of phishing is impersonation, pretending a trustworthy person, asking for credit cards, user credentials, or private information. It has a very low barrier because attackers just copy a real website, a fabricated website. And the techniques are now very fastly evolving, and sometimes they use the URL shortening to hide the real phishing URL. Then it's hidden, so it's likely that a user can click this phishing website, because URL shortening shortened URL itself doesn't seem harmful, right? And sometimes attackers steal the credentials by forwarding these credentials to an actual site. Then you enter username and password in a phishing site, and redirected the site is the actual. Then you do not, the victim does not doubt too much about the credential. And currently, attackers diversify the channels, trying to reach the victims by messenger or SMS. SMS phishing is particularly called smishing. And phishing is one of the very widely known as one of the social engineering attacks against the human, because the humans are often regarded as a weakest link. And these are the phishing examples. Sorry for non-English speakers, but these are just the phishing messages. So these guys impersonate Unlab, which is a security company in Korea, but which is not actually Unlab. And these are, the messages impersonating a mother. So if even though it looks obvious, the number of phishing victims increases every year. So you should always be careful when you receive the message from unknown, or even though you get the message from seemingly benign users. You should always be careful about particularly opening the messages and attachment, opening email. All right, other DNS-based attacks here, DOS on root servers. We could the attackers could amplify DNS attacks because DNS packet does not have authentication mechanism, and sometimes DNS communication can be used as one of the covert channel. If you think about the command and control server, the botnet sends the DNS packets. Inside the DNS packets, there is a hidden message, and it's possible to exfiltrate the data throughout this covert DNS messages. And John transfer. This is the one that I explained in previous slides. And DNS server bugs. These bugs can be exploited. This is system software security to compromise system. And there are various different attack goals. The attackers can hijack the script hosted on expired domains in use, or attackers can hijack the third-party libraries or modules of very popular language repositories like NPM or GitHub or PyPy, and attackers can re-register the expired domains because users do not know that the specific domain has been expired or not. So if the attackers can re-register the expired domains, then he could leverage the popularity of domain name into one's attack. This is slightly different field, but censorship. We have an era of censorship. It looks like we have the full freedom to access to the internet, but the real life is not. It's not true. Censorship is an entity that desires that some identifiable communication to be blocked from being transmitted over the network. So, for example, in Korea, we also has the censorship as well. So if you want to access, porn sites or illegal sites that sells the guns, or weapons, then these websites are automatically blocked. And the country has the list of blocking websites. Here, as I said, some countries has the censorship at a country level to block, CNN, Facebook, or YouTube. One of the good examples would be Great Firewall of China. They block all, Twitter, YouTube, Facebook for political reason. So one of the common ways to implement the censor is to block host names. Okay, so censorship is another example of domain name based attacks. So what can we do about this? DNSSEC, which is DNS security, as the name suggests, the goal of DNSSEC is slightly different. The main goal is to enable authentication and ensure the integrity of DNS requests and responses. So the objective of DNSSEC is integrity, not availability or confidentiality. So what the DNSSEC does is to cryptographically sign the resource records. Again, this RR contains the most important name serve the request message. I mean the information about the name, domain name, right? And the reservers can verify the signature, and then you can guarantee the integrity of the DNS request. So if you remember here. So currently you see very weird messages here, and actually this is the DNSSEC message. So somehow when this server receives this message, and this message has been signed by root server, and edu servers can verify this message with the public key of the root server, and the name server of SKKU actually receives this message, the DNSSEC message, and this message can be verified with the edu server's public key. And two new resource types here, DNS key and RR signature. And DNS key creates a hierarchy of trust within each zone, and this key and the public key is used here for the verification of signature. It prevents hijacking and spoofing. But this is not a complete solution. Please read why here. Still, it's possible to amplify those with the DNSSEC, and CPU adjustment tag is viable. Right, I think that's pretty much it for today. Thank you.